into the mall, and so they pulled me over for making a U-turn rather than a left turn there.
Are we good?
Yep. Let's go.
Okay, so I'm speaking on Deuring's theorem, and I plan to get to the proof of it, but if I don't, at least I'll get to the statement. Deuring's theorem equates an L-function of an elliptic curve with complex multiplication to an L-function of a Hecke character, so I have to answer this question. So what is a Hecke character? So here's sort of the idea, which we'll make precise in a second. So we have Dirichlet characters like so. We have sort of maps from Z mod n cross to C cross. And they give rise to L functions. That's why Dirichlet invented them.
Actually, Hunter King.
L of chi S. These are just functions on the complex plane. And the important thing about these functions is how do you define them? You define them just like with the Riemann zeta function, but twisted by the character chi, where if m is not prime to m, you just say chi of n equals 0. And exactly like the Riemann zeta function, these guys have Euler product decompositions. So these are just over the primes. And the important fact that they satisfy is a priori that series should only converge when S is large, when the real part of S is large enough. But these guys satisfy a functional equation. They have analytic continuation to the whole plane, and they satisfy what's called a functional equation, which I'll write down below. So we're going to say L infinity of chi S is gamma is Euler's gamma function. I think it's due to Euler, right? You know, it's gamma function, as always, times pi over m to the negative s plus a over 2, where a is what's called the parity of chi. So a is going to be 0 if chi of negative 1 is 1, and it's going to be 1 if chi of negative 1 is negative 1. It's kind of the parity of chi. And we say chi is even in this case, and chi is odd in that case. Right. So then, so if I just let L infinity mean that, and I let big lambda of chi S just be L of chi S times this extra junk that I just wrote down, then we have the equation lambda of chi S is lambda of chi bar 1 minus S, and I have to modify it by some sort of trivial coefficient. So I to the A times root m divided by what's called the Gauss sum of chi, which is related to what Alex was talking about a couple weeks ago. It's just essentially a Fourier transform given explicitly by this formula. Sorry, this actually be an m. Okay, so this explicit formula is not important for my talk. I just want to get across that the reason, so these guys have been around since the 1800s, and the reason that they're good is because, although a priori they should only converge on some right-hand plane, they actually have analytic continuation in a functional equation. That's all I need about these guys. Okay, so what's a Hecke character? So we want to generalize Dirichlet characters in two ways. So the first is, we want to view them we want to look not just at finite order characters, but sort of any map into C cross, and we want to see it as a map on ideals of some number field, not just ideals of Z. So let's say we have some psi, so we'll fix a number field F, and suppose we have some map psi going from the ideals of F to C cross. And it should be, it should be a homomorphism. Just like before, I'm not going to require that it be defined everywhere, right? These guys were only defined on ideals prime to m, and I extended it by 0 elsewhere. So I'm only going to require this to be defined on ideals prime to some ideal fractor f, which is called the conductor. And the question is, does it make sense to define something like L of psi s, which would be, so now I'm summing over all the ideals A of f, the integral ideals. Okay. And then it doesn't make sense to like take a complex number, which is a to some power, but I can take the norm of a down to q, that's a number, and then raise that to the s power. And then just by the formalism of ideals, right, every ideal's got a unique factorization. So this will still satisfy some Euler product if the function makes sense. Okay, so unfortunately the answer to the question that I just wrote is no. Okay? I know, right? So the point is that I haven't added enough conditions on psi for that guy to exist. So this might not converge, and even if it converges, it might not like have earned the right to be called an L function. Because to have the right to be called an L function, you really need to at least conjecturally satisfy some functional equation. And this won't in general, right? So we need an extra condition, and that was discovered by Hecke in 1918.
So you're summing over ideals prime to f?
Yeah, so if the ideal is not prime to f, we just let this be 0, just like with the Dewey equation. So we tend to be sloppy about that, and we'll continue to do so. Okay, so the refinement due to Hecke is the following. So given such a psi, we can get an L psi s just like before, provided that psi satisfies a certain condition that I'll call condition star. And so what is Hecke's condition? So Hecke wants the following. So remember we have this f where psi is not defined, and Hecke wants the following. If A is principal, and furthermore, the generator of alpha equivalent to 1 modulo the conductor, then there is a continuous map, so homomorphism, that I'll call psi infinity. I should really call it psi infinity inverse, but that's not too important. From F tensor R cross to C cross with psi of the ideal A equal to psi infinity of alpha. Okay?
Can we review real quick with psi converts to 1 mod f?
Alpha converted to 1 mod f means alpha minus 1 lives in the ideal F. That's all.
Oh.
No, in class field theory, you have to think about this a little harder because there might be infinite conditions of the ideal. That's probably what you're thinking of.
Yeah.
But in this case, it just means alpha minus 1 is enough. Okay. Cool. So this is, I didn't put a star next to it, but this is Hecke's condition, right? And so the problem with Hecke's condition is like, right, it's like, why? And Hecke's proof that this satisfies a functional equation is very difficult. In fact, he only initially proved it for cubic fields and said the actual proof is analogous and had to be pressed to produce the actual proof. So it's very difficult and unnatural condition. And the solution to this problem